A parent advisory board for a certain university was concerned about the effect of part-time jobs on the academic achievement of students attending the university. To obtain some information, the advisory board surveyed a simple random sample of 200 of the more than 20,000 students attending the university. Each student reported the average number of hours spent working part-time each week and his or her perception of the effect of part-time work on academic achievement. The data in the table below summarize the students' responses by average number of hours worked per week, less than 11, 11 to 20, more than 20, and perception of the effect of part-time work on academic achievement, positive, no effect, negative. Use a chi-square test to determine if there is an association between the effect of part-time work on academic achievement and the average number of hours per week that students work. So in this table, we have our average time spent on part-time jobs, and then we have perception of the effect of part-time work on academic achievement. And as stated in the problem, the part-time number of hours worked is broken down into three groups: less than 11 hours per week, 11 to 20, and more than 20. And then we have the perception categorized into positive effect, no effect, and negative effect. Now, the question is, determine if there is an association between the effect of part-time work on academic achievement and the average number of hours per week that students work. So the null hypothesis then would hypothesize that there is no relationship. So we would say something like average time spent on part-time jobs and perception of the effect of part-time work on academic achievement are independent. Then the alternative to that is that there is a relationship between the two categories. Now, what we're going to use in order to answer this question is a chi-square test. And just as before, the chi-square test is going to depend on how much do the observed values deviate from the expected values, because this formula is going to have us adding up a whole bunch of terms that look like this. We're going to take the observed values and subtract from those the expected values, and then square that, and then divide that by the expected values. Now, what we have in this table are the observed values. And because there are differing numbers of people that fall into each category, then the expected values will have to be determined according to those ratios. Now, fortunately, we have available to us the technology of the TI-84 calculator, which will calculate those expected values for us, but will also calculate the chi-square test value and tell us our number of degrees of freedom and so on. But in such a test as this, our number of degrees of freedom is the product of 1 less than the number of columns and 1 less than the number of rows. So in other words, in this case, we have 3 columns, less than 11 hours per week, 11 to 20 hours per week, and more than 20 hours per week. So that's 3 minus 1 times, and then 3 rows. Positive effect, no effect, negative effect. So that's 3 minus 1. So we wind up with 2 times 2, or 4 degrees of freedom. And just as always, we're going to need to come up with a chi-square critical value. If we use StatCrunch to do that, we could push Stat, Calculators, chi-square. Our number of degrees of freedom will be 4. And if alpha is 0.05 here, then we'll type 0.95 here if we leave this at less than. And that'll give us 9.488 if we round to 3 decimal places. So our chi-square critical value will be 9.488. Now we can use StatCrunch, or we can use the TI-84 calculator to find the chi-square test value. If we're going to use the TI-84 calculator, then what we're going to need to do, TI-84 or 83, what we'll need to do is access the matrix function. And when we get there, we're going to need to define the number of rows by the number of columns for a matrix. So the thing that we have to remember is that we have 3 rows and 3 columns here. So in order to access the matrix function, we'll push second matrix. We want to edit a matrix, so we'll cursor over, and we may as well just edit matrix A. We could choose any of these that we want, but we'll keep it simple, so we'll just push 1. Now what I said was that we were going to have to define the size of this matrix. It will be a 3 by 3 matrix because we have 3 rows and 3 columns. So we push 3, enter, 3, enter, and we're going to now see that this has expanded to that size. Now what we're going to put in here then are the values that were in that table. The way that it's going to do that is across, so it's going to use rows to do that. So we'll type 21, enter, 9, enter, 5, enter. And you see how it progresses through. So we'll now just finish typing them in. Now we have the entire matrix filled in. Now what the TI-84 calculator is going to do for us is it is going to not only calculate the chi-square value for us, it'll also calculate all of the expected values. And we'll do that by pushing Stat, and we'll go over to Tests. We want to go to the chi-square test, which will be C. And then it wants to know, where are the observed values? Well, we put them in matrix A. And then it wants to know, well, where do you want me to put the expected values? And we'll just tell it to put those values in matrix B. So we'll come down and hit calculate. And now we have our chi-square test value, 13.938. So our chi-square test value is 13.938, and we also have a p-value. The p-value is 0.007 if we round to 3 decimal places. Now, in either case, whether we use alpha of 0.05 and the p-value and pair them up, or use the critical value and the test value, we come to the same conclusion either way. We are going to reject the null hypothesis. Now, what does that mean? If we reject that they are independent, then we are going to assume then that there is a relationship between the two categories. Now, just so that we understand the process, let's go and look at the TI-84 calculator at matrix B and see the expected values. So we'll push second matrix, and what we want to do is look at what's in matrix B. So we're going to go over to edit, and then we're going to access matrix B. And these are the values that we would expect from the survey if there were no relationship between the two variables. Now, before we leave this problem, let's take a quick trip over to StatCrunch and see what the computer output for a problem like this might look like. On the AP exam, you may actually have a problem that looks like this with these observe values in a table, but you also might have the computer output already available to you so that you can make decisions quickly. So I've already typed the values from the table into this StatCrunch spreadsheet here. We'll push Stat, and then we'll go to Tables, Contingency with Summary. And then I'm just going to select these three variables. And then I'm just going to choose the first one. And then I'm going to click chi-square test for independence and hit compute. Now, what we see here then is this part of the output. So you see in the computer output then, we have the number of degrees of freedom, 4, which we calculated over here. We get the value of the chi-square test, which we have here, and we get the p-value, which we have here. So sometimes, in addition to the table, you might get this table with the computer output that allows you to do the same analysis without doing the calculations. You will therefore need to make appropriate comments. In addition to being able to state the hypotheses and perform the analysis, you might also be required to make some comments regarding the requirements for the chi-square test. As always, in any sampling situation, the condition must be met that all subjects were randomly selected. And in a contingency table problem such as this, it is also required that the expected cell counts should be at least 5. And when we go back to matrix B, which contained all of those expected values, we find that the smallest cell count is 6.825. So this condition was met. You might also be asked to comment on the possible error that has been made. Well, since the decision was made to reject the null hypothesis, then the possible error would be a type 1 error. Remember, a type 1 error occurs when you reject a true null hypothesis. So it's possible then that we would conclude that there is a relationship between the two categories when in fact there is no relationship between the two categories.